Hi, today we are going to talk about Elec207 lecture 12 noise and interfaces. So the signal processing part, measurement signal is often produced by the extract the relevant information or to clean by moving noises by other disturbances. There are two types of signal processing. The first one is analog signal processing, which is related to analog digital signal. A typical signal is to filtering by removing the noise before the ADC. And the other one is, I think, is it what kind of signal? High pass filter or low pass filter? High pass filter, low pass filter. And a typical example of filter to remove noises. And then the digital signal processing is applied to a digital signal after the ADC. Typical example is calculation of the RMS or of the transformation of the signal in the frequency domain and so forth. So additionally, we are going need to consider the noise. The noise is undesired disturbance superposition with the measurement signal, which is affect the quality of the signal. The quality of the signal can be measured by the signal to noise ratio, which is the ratio between the signal power and noise power. The noise in the measurement system forms two forces, which is internal and external. The internal one mainly is the thermal noises and the interfaces of other circuits. So in this domain, we mainly talk about the external one because the internal one is hard to quantify, and so the electronic interference from external power circuits is quite common, commonly from the industrial environment. It is caused by the inductive and competitive coupling between the measurement circuit and other circuits near it. It typically produces noise at a high frequency. So you can think about it like that. If you wanted to that you're measuring how much voltage did you generate by waving through this this handle, and you're thinking about that. So if you are moving very fast and you have a very high voltage, right? And when you are moving very fast, you are going to have a very large noise, right? And that's basically the principle behind that. Because you are moving at a high frequency, you have a higher voltage, and the measurement of your voltage will be generated with some noises. So additionally, the coupling and can be decreased by separating the measurement circuit from other circuits, but it's not always possible. For example, when the measured quantity is the power of the measured quantity in the power circuit itself, therefore other solutions are required. Can be decreased by separating the measurement circuit from other circuit. Yes. For example, we are going to talk about the inductive coupling, which is the cause of the problem. In a sometime varying magnetic field, which is originated in the power circuit, and near the measurement circuit may induct the voltage in the measurement circuit due to the inductive coupling. For example, this is AC voltage and AC power supply, and when it goes to an inductor, the derivative of the AC circuit is proportional to the induction flux that is generated here, and based on the derivative of based on the induction flux and the induction flux within this coil will be proportional to the voltage that is generated. Therefore, so this one is the signal generated one, and this one is the signal circuit, which is going to be illustrated as the transducer together with the amplifier, because the transducer will only measurement the signal, only the amplifier will make the measurement more clear, easy to read. So apart from the coupling there, this is the desired coupling we want, but we also have some maybe coupling that's generated between lines. These lines will also generate the magnetic flux. So how do we eliminate the magnetic flux that is generated between the measurement circuits? So we can twist the two lines. For example, look at this one. So the voltages in that one, based on the right-hand rule, you will see that based on the right-hand rule, this is that direction. And look at that. This is sorry, it's my mistake. So based on this is coming out, this is coming in. Based on the right-hand side rule, this is in the dot, and in this one it is in this one it is coming in that direction, and in that one it is coming. 对吧？哎，不对呀。Just a moment, and it was noticing that this is coming that direction, and this is coming that direction. Oh, look at that. This is not intuitive now. Look at that. So this is in that direction, and this is in that direction. And on the right-hand side, this one will give you this, and this one will give you this. Right. This is correct. But because it is twisting, so these two will form a zero magnetic flux. Right. 哎，对呀。这是负的，这是负的吗？负的会往，这是负的，那肯定是对吧？负的电流方向是往这边走的，这正的电流方向往这边走。这样的话，你大拇指指上电流方向，你就这是往里面指，这个，怎么也是往里面指？关键是，那你看。这层也是往里面指，这个也是往里面指。This is very interesting. I will talk with lecture about that. And another thing, it should have the desired positive effect, where the looped area is reduced to the minimum, and the voltage induced by the adjacent loops are positive. So the balance out the overall inductive voltage to be zero. And apart from the inductive one, we also have competitive coupling, where the wires are conductors, so there's always a competitance between wires in different circuits. This competitive coupling may induce voltage in the measurement circuits. For example, in these cases, the inductor here is actually the line here, and the noise here is actually the noise from the other circuit, and the ground is the ground here. So because every line can form a line between line can form a kind of inductive competitive effect. So there's a competitive here, there's a competitive here, and therefore the inducted voltage due to the competitive coupling is always common mode voltage, which is the same as two lines, which is the same on the two lines of the measurement circuit. Therefore, it can be easily removed by the differential amplifier. So that's very common, because Z line has some effects, and Z line has some effects, and we can only look at the differential of these two lines, which is going to be using a differential amplifier. The effectiveness in removing competitive coupling is measured by the common mode rejection mode. The common mode rejection mode is rejection ratio is actually specified in the document, and we can which is this ratio is the between the differential voltage amplification. This is the thing that we measured, and this is the thing that we want. We have known the ratio, we can get this one. And the instrument amplifier have very high CMMR. This is very good because we are going to have this is very low and this is very high, then the ratio is very high. Okay. And another thing is the competitive coupling. The thing is that it is going to use a shield cable. So this one is inner inductor, which is zero. For the inner conductor is just this one. This is 0, and this is 0, and this is also 0. So therefore it is 0 in total. 0 voltage, which will make there's no electricity, there's no magnetic flux. What if there's no magnetic flux? This will only create the CS as the desired. So how do we eliminate the CS actually? How do we eliminate the CS? Okay. The shield can either be negative terminal based on the third conductor. And another thing is about the ground loops. Another source of possible noise is represented by the multiple grounded points, because every part of the circuit may be grounded to a point. However, it is ideal. What if they are not grounded at the same point? There may be some generated wire and maybe the column in the ground, which may cause some effects. The solution is that we are going to put it into the ground at the same place. Okay, that's all. Thank you very much.